Okay, so we decided that this problem was going to be indeterminate form because it gave us 0 over 0. So something really key here that you may notice is that I did not write equals 0 over 0. We cannot say that it equals 0 over 0. The reason why is because we are going to be trying something else, eventually we will get a different answer. So by saying this limit equals 0 over 0, but then later on saying it equals something else, we are giving conflicting information. So a lot of the times we can get away with saying this, or we can just go ahead and do that other method. The really nice thing about direct substitution is that if it doesn't work, we don't actually have to write anything down. So we can kind of do that check in our heads or on our calculators before we actually write it down. If it works, then we can just write it down. If it doesn't, we already have to try something else anyways. So when I look at this, what I notice is that this 0 in the denominator needs to go in order for us to get an actual number. We can get undefined as an answer, which means our limit won't exist, but we have more x's on the top than we do the bottom, so there's a good chance that we can kind of just get rid of some stuff. So we have a couple options for how we can format this. One way that we can do it is by claiming we have side work. So I'm going to go ahead and write side work over here, and I am going to take this function and move it around. So the thing we have here is x to the fourth minus 5x squared over x squared. So one thing that I'm going to do is try to factor as much as I can. One thing that I'm trying to factor here is what things have in common. So if I look here, x to the fourth and 5x squared have x squared in common. So I'm going to go ahead and pull out an x squared from everything in the top. So if I'm figuring out what multiplies to get to that, x squared times x squared would be x to the fourth, and x squared times negative 5 is going to give me this other piece. I have not actually changed my equation, I've just changed what it looks like. This next part, though, is an actual change to the problem. So normally we look at this and we go, hey, x squared cancels out here, and it does. But we have a really hard time here saying equals. And the reason why is it's not technically equal. It's equal at every point except a certain value. So instead of using an equal sign, I'm going to go ahead and use an arrow. So we get this left over, x squared minus 5. And the one key thing here is x cannot equal a very specific number. That number, it happens to be the same as our limit, which is 0. I know that because that's what would make the denominator equal 0 and what's causing us this issue. So now that I know this, I'm going to go ahead and find our limit, but we are going to use this equation instead. So what we're going to do is, normally we would rewrite it the original. This is the problem that we're solving, so when we rewrite, we're rewriting it just so that way we're saying, hey, we were solving that original problem. So we're saying this is equal to the limit as x approaches 0 of x squared minus 5. So one thing that you may notice is that I wrote that limit notation again. We cannot drop that limit notation until we have applied our limit. Applying our limit means that we are using direct substitution. If we get indeterminate form and direct substitution didn't work, then we have to keep using that limit notation if we are physically looking at that limit. Now, my side work, on the other hand, I can do side work by itself without having to write a limit, but I just have to make sure that I'm pretty clear about notation. If I added limits here, I don't need to worry about this weird equal sign and some stipulations. So I'll show you what that looks like in the next one. So now I'm just going to use direct substitution again. I have a new problem that we're looking at that's equivalent, but maybe not exactly the same. So we're going to go ahead and plug in 0. So we have 0 squared minus 5. And we can say that is equal to 5. So our limit overall is equal to 5. And if we were to look at that graph, we would see that there is probably a hole and our lines are going towards the same value, 5. Okay, so we have another one over here. If I were to do direct substitution really quick, let's see what we get. So negative 2 squared gives me 4, 3 times 4 gives me 12. Negative 2 times 5 is negative 10. And then we subtract 2. So the top for sure goes to 0. Negative 2 plus 2 is also 0. So this is another indeterminate form where we get 0 over 0. Okay, so this time I told you that I would show you what it would look like if we never got rid of the limit. So when we are doing it this way, we can actually just go ahead and put an equal sign, an equivalency here to kind of help us out. But every time I put an equivalency and I have not used my limit, I need to make sure that I write that limit notation. So the limit as x approaches negative 2. Well, we can't factor really anything in the bottom. There isn't any squares to be able to factor out. And the good news here is we got indeterminate form, so I already know what needs to go away, which is this x plus 2. So that tells me x plus 2 has to be a factor of what's in the numerator. So we are going to be kind of factoring this out. So things that I know. We are going to have something with x plus 2 here because that is what's going to have to cancel out. The other piece here we have is the other part. Well, x times 3x is what's going to give me 3x squared. So I know this is going to have a 3x. And whatever is in this last piece here multiplied by whatever's over here is going to have to give us this negative 2. We already have a 2, which means this has to be a minus 1. If this didn't make sense, factoring is what we're going to have to work on. So you don't have to do this method for factoring that I just did. That is just from me knowing what the problem looks like, a faster way of working with it. So box and diamond works great. Factor by grouping works great. Whatever works for factoring for you, that's what you need to do. So I'm just going to double check. If I do 3x times 2, that gives me 6x. X times negative 1 is a minus 1x. If I combine those two, that does give me my 5x here. So if I were to multiply these out, these two things are equivalent, so this is an equivalent state. So now that I have this, I can go ahead and say, hey, we have a common term on top and bottom. I can cross this out because I have this multiplication right here between our two sets of binomials. Binomials meaning just two terms. And I can rewrite my statement. Because we are talking about a limit versus just a function in general, I don't have to worry about making any stipulations because we're saying, hey, these are exactly the same. These lines move in the same ways. So I am now looking at the limit as x approaches negative 2 of 3x minus 1. So if I were to plug in negative 2 for x, I get something that looks like this. 3 times negative 2 is negative 6, minus 1 is negative 7. So we are getting something that kind of looks a little bit less complicated when we factor, and that's kind of the goal here. So when we look at these two ways, they are similar but different. The big key for if you want to keep the limit in is that you need to make sure you write the limit until you apply it, which is plugging it in using that direct substitution. Otherwise, if we do these side works, we need to be a little bit careful about what we are saying is equivalent to what. So that is where this kind of gets us in a little trouble. I personally like this method better, but this tends to be forgotten when we use this method. Okay, we have one more problem here, which is the limit as x approaches negative 1 of x cubed plus 1 divided by x plus 1. So here's the thing. If I were to plug in negative 1 cubed gives me negative 1, negative times a negative times a negative. And if I were to add 1 together, that gives me a 0. Negative 1 plus 1, also 0. So we have indeterminate form here again, which means that we need to do something else. We have to try something else. Factoring is only going to work if we know how to factor this. So sometimes one of the things that we may want to do is polynomial division. There are lots of ways to do polynomial division, but if we're talking about the fastest for AP, the fastest is synthetic division. So we have this right here. Because we got 0 over 0, that tells me they have a like term. 0 over 0 is going to tell us that it's going to give us a whole every single time. So, because I know that, I know x plus 1 is a factor of what's above, which means if I want to use synthetic division or polynomial division, what I'm really trying to figure out is x plus 1 divided by x cubed plus 0x squared, because we need those placeholders, 0x's plus 1. This is just regular polynomial division. It works absolutely fine, and if this is what you're comfortable with and you know how to do it this way. If you have never seen it before, I am going to show you synthetic division. It will give you the exact same answer, but there is less kind of stuff that you need to do. So the big key with synthetic division is the setup. So you always have a half box. In the half box, we are realistically solving what makes the thing that we think is a factor equal to 0. So if I were to do that and I solve for x, this gives us x equals -1. So -1 is going to go in this box, and it's kind of the most important box that we have here. So for synthetic division, just like regular polynomial division, we need those placeholders. So I have x cubes, I have x squareds, x to the first, and these ones category. So I have 1x cubed, I have 0x squareds, I have 0x to the first, and I have 1 in our ones category, things without x's. I'm going to draw a line and some things that you need to know. We are going to be doing the same operations over and over and over again. So if I am below the line, I'm going to be taking these things and multiplying it by -1. That is going to go in this area. Once I have something here, we are going to be adding. So because there is nothing below the line yet, the first thing you always do is drop that first term. Well, this first term happens to be 1, so 1 has to go below the line. Okay, now is where we multiply. So we take 1 and -1, multiply them together, and we put that product underneath the next empty spot. Now we add. So 0 plus -1 is -1. -1 times -1, positive 1. 0 plus 1, 1. 1 times -1 is -1. 1 plus -1 is 0. This right here is the important piece. If it is a factor, this last number will be 0 because this is our remainder. Now, the hardest part here is understanding what happens to our answer. So when we're looking at this, originally we had these as our categories. But if we think about it, what we divided by was an x. So if I had x cubed and I divided by x, that is now going to be x squared. So our answer is based off of being 1 less than it was before. So these are now connected. So when I write this, these 1, -1, and 1 are my coefficients. So I have 1 and x squared. I have -1 x plus 1. And I don't need to write the ones, so we would probably see something kind of more like that, which would be our answer. So what I know now is this is what would happen if I divided these two things together. So what I can say now is equals, I haven't applied my limit, so I'm going to write limit as x approaches -1. If I were to divide x cubed plus 1 by x plus 1, this x squared minus x plus 1 is my answer. On the other hand, if you want to go the factoring method, what this also means is if I were to take the answer we just got and multiply it by x plus 1, this would equal x cubed plus 1. So I could go ahead and substitute this piece in to the top of my fraction instead, and then divide out the common term. Personally, we already did the division, so it just feels easier to write it out this way. So we have done the division. We got an answer of this new function. So I am going to write that down. So we have the limit as x approaches 1 of x approaches negative 1 of x squared minus x plus 1. And now we're going to use direct substitution. So we're going to go ahead and plug in negative 1 into our answer. So negative 1 squared minus negative 1 plus 1. Okay. Negative 1 squared happens to be 1. If we subtract a negative, it is technically a positive. And by technically, I mean it is. And then we have a plus 1. 1 plus 1 plus 1 happens to equal 3. So the limit as x approaches